All right, we are back again, and we're now going to be going over code types and writing codes. And if we get enough time, we'll finish up with how to convert codes into the next patch. So first things first, you'll remember this from the last video. This is our Zenny cheat. Um, we went over these uh, values on the right side. This was our pointers and offsets, and then this was the value we were changing to. Today, we're going to be going over everything on this left side. All right. So how codes work is through storing a value into a memory address. All right. And these values here is telling the switch operator or the atmosphere or whatever program you're using. This is what's telling how to do that to the OS. So first things first, we have code types. Code types are always this first value right here. They go from 0 all the way up to F. Yeah, so they go all the way up to F, and then with some special codes in here. We're really just going to be covering the first 9. Um, I've not seen anybody use a code 10. I think they're starting to become more popular, but I haven't seen one yet. But starting with 0. All right, code type 0, storing a static value to memory. You'll see these commonly used with writing codes towards the main instead of to heap. Um, I don't think this can deal with offsets very well. For an example, we have infinity 100%. So I can see we have the 0, and what that does is it tells it the code type, and then every code type has a special reference, right? Each one of these is going to do something different. So the first one, I should say the second value, is always going to be pretty much the width of the memory you're going to write, how many bytes. Um, Now, depending on what you're trying to do, you may need more or less. Um, Usually for bigger values, you're going to need more bytes. Um, Otherwise, it won't be able to convert that number into an actual value into the memory. Um, Third value is the memory region. Like I said, 0, so we can see 0. If it was a 1, that would be writing to the heap. Then we have R for our fourth value. This is register offset for the memory region. Again, we have a 1. Um, these will change. I haven't found anything definitive on how much this changes, but I've seen everything from 1s to 2s, 4s, 8s, and Fs. I see a lot of people who write F, and I assume they just want maximum value, just get it over with. Um, if you're creating a cheat for the first time, I would play around with this, and I would play around with this. The second and the fourth seem to be able to do more than I'm seeing as far as fluctuation in cheat codes, and you'll see that here shortly. You'll see a lot of people you will use 8 or F. Um, and again, I'm not 100% sure if we understand what that's doing or if people just like, well, I've always used this and it's always worked. Might as well keep going. All right. Moving on. So this second line, that's going to be this. As you can see, we have 0, 0 here, and then we have an actual value here. This is a direct memory address. If we were to throw this into an expression, you would see 3 zeros and then the code. Well, check that out. That goes straight there. So we know that this is the direct memory address. So like I said, I don't see how a proper offset can be used just with this single code. You'd have to do stuff before this, before you got to that. And we'll go over that in a minute. All right. And then from here, we have the value. All right. And as you can see, we are writing that. Moving on, code type 1, begin conditional block. These I haven't seen very often. I have no examples off the top of my head or in any of my files right now. But I think this is a more useful thing than people realize. Um, so what this can do is it can check a condition, right? So something like, if this address falls below this value, do this. Um, so for an example of that, let's say you have 100 HP, all right, and at 20 HP you want to start a invincibility frame, um, or even, hey, reset your HP to 100. That's a nice simple one there. We don't have to change addresses. Um, so if this value gets below 20, so if HP gets below 20, set HP to 100. All right. So now you have a cheat that doesn't look too much like a cheat, but it's still useful. So again, second value is your memory width. Third value is the region right. And then fourth value is where each one of these starts to change. Usually, this is very specific to what code type you're using, and it can be very useful to what you're trying to do. So for this one, it's C. C is condition to use. And here are your conditions. So we have greater than equal, less than equal, equals, or not equals. And then we have our address and value. All right, code type 2, end conditional block. These are good for both code types 1 and 8. You'll see this very common with code type 8, which is button press. And this just simply ends whatever the conditional block is. All right, code type 3, start end loops. Again, I don't see this very often, and the ones I do see are usually, I wouldn't say unnecessary, but I don't think people are using them as well as they could be. A lot of these, for example, I saw one the other day for heavy bow gun, the ammo. The person was using a start end loop to set a value of 3 into the ammo and just keep refreshing that over and over again. But they wrote it as a static address, so it shouldn't change. But they had the loop in there just in case. Without dissecting that code, I can't tell if that's needed or not. But my first instinct is probably not, unless there's something else going on in the game that is forcing that change. For example, if you use a special shot that uses all your ammo, well, that would reset your ammo to 0, and the code would have to then re-plug in. And the only way to do that would be, say, start end loop. Again, not a heavy bowgun user, so I'm not quite sure what's going on there. All right, codes 4, 5, and 6. These are almost interchangeable. They're all trying to do the same thing, but just different methods of doing the same thing. All these are your storing storing a value into a register. So, for example, code type 4, I see these quite a bit. This is a constant value. You just set this and forget it. This should not change unless you get something where, for example, a game mechanic takes away everything from you, whether that's money or something else. Like that could overwhelm this. Loaded register with a memory value. Again, I see this sometimes. Usually this is for using the pointers. So it is useful. And then moving on to code type 6, this is storing a value into a memory address. So this is usually common. A lot of people use this for the cheat itself. And that's why I think some people could be using something different, like a code type 4 or even a code type 1, depending on where it's at. I'm sorry, not a 1, a 0. Yeah, code type 0, not 1. All right. Anyway, this is your most commons. All right. Like I said, pay attention to what's going on. Like I said, code type 4 is very generic. If you get all the way through the pointer and you are just writing a static value, you should be trying to use this as far as I'm concerned. Like I said, I see some code type 5s and some code type 6s. Code type 7, People usually use this to end the offsets for their pointers. What this can do is it can perform an arithmetic function. So addition, subtraction, multiplication, left, right, shifts. And honestly, like I would try to start getting away from 7. Code type 9 seems to be a lot more valuable and a lot more robust. Code type 8, here is one of the most common ones I see used both correctly and incorrectly. So code type 8 is your conditional button press. So if you want to say, use this button combination to do this address value change, this is what you'd be using, all right? So for example, of all these code types that we've gone over, I have refill sharpness. So as you can see, we have a code type 8, all right? So this begins our conditional key press. Now, if you look, everything rest in that block is the keypad mask. Now, you can set multiple keys to accomplish this. All right, and as an example, we have 8400. So let's take a quick look. Oh, there's our 8,000. So that's our down, but we have a plus. Well, where's our plus? Oh, here it is. Okay, so 8, 4. Now, you can set multiple values here. So for example, we have ZL, ZR, plus, minus. All these share this, all right? But this is written as in bytes. So this is actually very useful because you can sit there and go, okay, if you have a 3, well, that's ZL and ZR, right? These two together. Or if you want plus ZL, well, that'd be 5. And as you can see, none of these values can ever overlap each other. All right, that's on purpose. Remember, this does go up to F. This is a hex code. All right, that covers code type 8. And remember, with a code type 8, you need to end it with a 2. All right, as far as the rest of this, as you can see, we have our code type 5s, and this person used Fs, and they are setting up their pointer all the way through here. Then we have code type 6, and it is writing a value of 5. Now, if I had to guess, that's going to be a sharpness value, since that's a very low number. So that would be your different colors of sharpness. And then we have a second offset. We're performing arithmetic. We are adding 4. In fact, let's go back to 7. So addition, type RC. So the fifth value, 1, 2, 3. Yes, so we are adding 4. So we're adding 4 to the offset, and then we're changing that value to this. And then we are doing another 4 addition and setting the value to this. Again, if I had to guess, these are probably the sharpness bar itself. So how full it is. One of these is probably a max, and the other one is probably the set the value of. So we're setting it to full, and we're identifying that it is full and setting it to full. All right, moving on. Code type 9, like I said, this is our replacement for 7. Like I said, this can do a little bit more. This can actually do logic. So, like I said, if you can, I would start using this. This one, again, has a similar setup to the 7. But like I said, the biggest point is that it has more arithmetic values than 7 did. Yeah, 7 only has 5. All right, code type 10. I think this is going to be the new 456. Like I said, it does very similar things. It looks like it does everything that those do, all in one code type. And that starts with an A for being 10. All right, that's the basics of code types. All right. So we're just going to look at a couple of code types and see what they do here. All right, so this is a game speed. All right, so as you can see, this is a very low offset. Well, not too low. So this is probably right after the character values. So we have a code type 5. This is setting up our pointer. Code type 7 gets the correct address, and then code type 6 is our default value. All right. So this is probably game speed 1. And then we end the conditional block. Now, this is what I was talking about, some people writing unnecessary code. This code type 2 is completely unnecessary, in my opinion. What is going on is when you hold L3, which is this, it will write this value at these addresses, which are the same as this. So as you can see, bam, bam. Okay. So all these are the same, and these are all the same. All right. But this is the default value. But when you press the key, it writes this. Then, once you let go of the key, that kicks in, and it goes back to this. So personally, I think that's unnecessary. Maybe I'm wrong, but I seriously doubt it. Because this has no conditional block it is referencing. There is no conditional block up here. There's no type 1 or type 8. So I don't believe this is do anything. And we can check that later. Moving on. Oh, okay, so reversing cheats. Okay, so if, for example, we have patch 3.0 coming out for Monster Hunter Rise. Now, a lot of people are going to be helping writing these cheats, but we have to update the pointers. Pointers can change between even minor patches. How much they change, that is the question. For example, going from 1.1.1 to 1.1.2, probably not too big of a change. Some of the pointers could have changed by just a couple of addresses. But if we get a big update, for example, like 2.0 or 3.0 or hopefully 4.0, these can change significantly, especially if they're towards the end of the memory. So if you get something that's towards the end of heap, that could change a significant amount. But even at the beginning of heap, depending on how much they add to the main, usually not too much, but yeah, I've seen some pretty small patches throw some codes into disarray. And then also I've seen very large patches which don't change cheats at all. I remember seeing a game fairly recently that I think it was actually Xenoblade Chronicles 2, where a patch came out and added a bunch of content, did great things, but nobody needed to update their codes because they literally reference the exact same pointers. So these are useful things to keep in mind. It's probably easier to start off with something that's fairly easy and at the beginning of heap. So for example, things like player stats. So player HP is probably towards the beginning of heap. Player position, stuff like that. Those are probably going to be fairly close to start a heap. So you'd start on that and see if those change. And then as you go down further and further, you can see where the offsets start moving. We're going to do charge blades because, or dual blade charge value. This should be a little bit easier to demonstrate and hopefully won't completely wreck my game. All right, so first things first, we want to find the memory address that we currently have. So we've been looking at the wrong value this whole time. So let's let demon mode fade. Okay, as you can see, this number is starting to go down. All right, as our bar depletes, this is going down. So we know now this is our actual charge bar, which is correct. But for whatever reason, memory viewer pointed us to the first address and not the correct address. So my bad not catching that. All right. So we do know this is now a good value. All right. And we can verify that with this code here. So we enter that, we poke it, and when we resume the game, that should be go back to a full bar. Bam, full bar. All right. So now we understand where to find this value on our current system and how to change it. And that's what's important about the next um, patch that's going to come out is we don't know how much this is going to change. But if we can reliably find where this value is stored, well, then we don't have to worry about um, trying to find it. We can just find it again and then update this pointer, and the code should still work. Um, these can be pretty generic. A lot of people will use the same codes over and over again, and I don't see a problem with that. But personally, I think it's sloppy. I come from a more structured background where you only use what you need. Anything more than that can get code that is ambiguous, hard to debug, and stuff like that. So it's always better to narrow your code types. Um, but that's just my personal opinion, my background. Um, so there's our demonstration that works. So yeah, so that's the basics of updating for a new version. Is you're gonna need to refine your pointers, um, but your codes themselves shouldn't change, um, and your values shouldn't change. So really, between updates, the only thing we're really worried about is our pointer and our offsets. Um, if there's any questions, ask the channel. I'll go over anything I can. But I should mention code types here are probably my weakest. Um, Coming from the PC world, I am used to just direct injecting values into a memory address. I don't need to tell the operating system how to do that. Um, so something to keep in mind. There's a few guys in the channel that are helping out that are really good at this type of stuff, and I'm glad that they're watching because I, like I said, they probably know more about this than I do. Um, but as far as finding pointers and stuff like that, if you guys need advice or help or whatever, just ask in the channel. Let's see if we can help each other. All right, that's it. Have a good day.